Hello students, welcome to the class. So today we will see the theory part 10 of the chapter chemical bonding and molecular structure. In this we will cover the section 4.8 and 4.9. So our objective would be today. So before going to the objective, this is the disclaimer. So our today's lecture objective would be to describe the molecular theory of homonuclear diatomic molecule. Now by homonuclear we mean that both the atoms of the molecule are identical. So if you are taking one atom as hydrogen, the second will be the same. Similarly, if you are taking a lithium molecule, then and then only we will be able to decide the molecular orbital diagram for the same. So those are simple to draw as compared to the heteronuclear diatomic molecule or heteronuclear polyatomic molecule, where we have multiple types of atoms present in our molecule. Now, after covering this part, we will see the concept of hydrogen bonding. It's very important from your JEE point of view and for your NEET point of view also. So why I'm saying it? Because this concept is not only used in the chemical bonding and molecular structure, this will be used in your periodic table, this will be used in your S block element, P block element, organic. So it is very, very important to understand this hydrogen bonding. If I list the topic according to the NCERT, so first we will cover the NCERT section 4.8, which is bonding in homonuclear diatomic molecules. Then we have a question of exercise, I would say the chapter and exercise of the NCERT, which is 4.36. So this question is basically covering all the parts of your homonuclear diatomic molecule type, where you will see that how does the bond order and bond length changes according to the molecular orbital diagram. Then next, in the last, we will see the hydrogen bonding, which is NCERT section 4.9. So let us begin our discussion. In our previous class, we have already seen the formation of hydrogen molecule, but we have not redeemed the information that this molecular orbital diagram is giving. So let us try to redeem all of those information. So we know that our hydrogen atom has 1s orbital. If you take a hydrogen atom, it has 1s orbital. Now its configuration will be 1s1. It's very simple to write the atomic configuration for hydrogen. It will be simply 1s1. Then if you are taking a molecule, then there will be 2 hydrogen atoms and each of this will contain 1 electron. So there will be total of 2 electrons. So this is mentioned here. We have an atomic orbital for 1 hydrogen on the left hand side and similarly on the right hand side. So both are 1s and 1 electron is present in each of this orbital. Then we'll start filling the molecular orbital. So what will happen? Both of these orbitals will combine and it will give us sigma 1s and sigma star 1s. Why are they combining? They are of the same energy, they are of the same symmetry, and they are combining to give us 2 different molecular orbital, because we are combining 2 different atomic orbital. So as a result, we are getting a bonding which is sigma 1s and anti-bonding which is sigma star 1s. Now we have 2 electrons here. Both are present in 2 individual atoms and we have to fill these 2 electrons in our obtained molecular orbital. Now we have 2 molecular orbital for hydrogen molecule, which is bonding and anti-bonding. And we know it very clearly that your bonding molecular orbital will have a lower energy. So in accordance to the above principle, we will fill the bonding molecular orbital first. Therefore, we are filling the 2 electrons in the sigma 1s. Now, if we fill this, because your anti-bonding molecular orbital is of higher energy, therefore, we will get the configuration as sigma 1s2. Now, your electron is not present in the 1s. Instead of that, it is present in the molecular orbital whose name is sigma 1s. We have already seen the shape of the sigma 1s. If you are unable to remember it, please, after the class, go and see it. It's very important. And then only you will be able to understand this part, right? Okay. I hope you got this point. So we are already there with our electronic configuration of the hydrogen molecule. Now we will try to use this configuration to obtain various information. So what are the information that we will get? The first information will be of about the bond order. It's very simple to calculate the bond order. What is the number of bonding of electrons present in the bonding orbital? It is 2. We can see it. It is present in the sigma 1s, and in the anti-bonding there are no electrons. Therefore, its bond order will be 2 minus 0 by 2, which will be equals to 1. So this is the formula for the bond order. We have already seen it in the previous discussion. Nb minus Na by 2. Now, since the bond order is 2, so there is a single bond between the two hydrogens, and that bond is sigma bond. Now, this is the normal trend that is seen in most of the molecule. So first, if there is a multiple bond, first there will be sigma bond, and then the consecutive bonds will be the pi bond. But since it is a molecule of only one type of bond, so it will be the sigma bond. Okay. So we can say that your atoms of hydrogen are covalently bonded by a single covalent bond. Now let us try to understand the magnetic nature. Since there are no unpaired electron, now which unpaired electron we are considering? We don't have to look at the individual hydrogen atom. We have to look at the electrons that are present in the molecular orbitals. So there are 2 electrons present in the molecular orbital in the same orbital, which is making both of the electron paired up. Therefore, this molecule overall will be diamagnetic, and it will be weakly repelled by the magnetic field. I hope this point is clear to you. It's very important to understand and derive to this final discussion. So whenever you are drawing the molecular orbital diagram like this for any other molecule, try to write each of the information that you are getting. Try to write the electronic configuration, try to calculate the bond order, and finally derive the magnetic nature of your given molecule. In that process, you should be also aware that the bond order that you are getting, it is indicating what? Your magnetic nature that is being obtained, what is the meaning of that, and what is the significance of your electronic configuration. Now, I hope you understand that how to do it for the hydrogen molecule. We will move to the next higher molecule, which is formed by the helium. So, from our previous discussion, I guess it is very clear to all of you that helium is a noble gas. So, it will be that molecule that wouldn't exist at all, because helium has already a complete octet. Now, this thing can be easily explained with the help of its molecular orbital diagram. So, let us try to draw the same. So, we have 2 helium atoms, and each of these will have 2 electrons in their 1s orbital. Now, the atomic orbital having 2 electrons will result in the electronic configuration of each helium atom as 1s2. So both of these helium atom will have an electronic configuration of 1s2. Now there are total of 4 electrons which are to be filled in the molecular orbital, 2 coming from each of the helium. Now what we will do? We will fill them. So where will the electron first go? It will go to the sigma 1s. So first electron here, then second electron with the opposite spin. Now once your sigma 1s is filled, then we have moved on to the sigma star 1s to fill the remaining 2 electrons. Now this will result in the electronic configuration of helium 2s, sigma 1s2 and sigma star 1s2. Okay. If this is the electronic configuration, now let us try to calculate the bond order. So our next target is to calculate the bond order. The number of bonding electron or the electrons present in the bonding molecular orbital will be 2, and also in the anti-bonding molecular orbital, the electron count will be 2. Therefore, we can calculate the bond order with the same information, and what we get the bond order as 0. So this is already assumed, or I would say this was already expected from the helium-2 molecule, that there will be no bond between the 2 helium atom as they have a complete octet. And this thing is completely explained by your bond order, that there is no existence of bond between 2 helium atoms. If the bond order is 0, then what we can say? That your helium-2 is unstable and it will not exist at the first place. So, do we need to care about the magnetic nature? No, we don't need to see that, because the molecule is itself not existing in the real world. Okay. So, with this, let us move on to the next molecule. Our next molecule is lithium molecule. Now, what do we know about the lithium molecule? So I would suggest you one thing while I am trying to draw the molecular orbital diagram, that you do this same practice along with me. Okay, try to draw the molecular orbital diagram as I have drawn in this, say you're given our deck, and fill the electron along with me. This will help you a lot and create a practice hand for your creation of this molecular orbital diagram. So it's very, very important to do this thing, to do this session along with me. Now, we know that your lithium atom has 3 electrons in total, where the electronic configuration of lithium atom can be written as 1s2, 2s1. So 2 electrons in the 1s and 1 electron in the 2s. It's very simple. 3 electrons are there in the 2 orbitals according to the Verb principle. Now, total 6 electrons are to be filled. The question arises, are we good enough to take only 1s and 1s? No, because your lithium has a 2s also. So there will be a new linear combination of atomic orbital, where your both 2s orbital will also overlap to give us sigma 2s and sigma star 2s. Now remember, student, your sigma star 2s is an anti-bonding, whereas your sigma 1s is a bonding. Okay. Similarly, your sigma 2s is a bonding molecular orbital, whereas your sigma star 1s is an anti-bonding. But we are seeing that the anti-bonding is having a lower energy, that your sigma star 1s is having a lower energy than the sigma 2s, which is bonding. Is it correct? Yeah, it is correct, because this time we are not considering the molecular orbital formed from the same atomic orbital. Instead, sigma 2s is formed from the 2s, whereas sigma star 1s is formed from the 1s. So therefore, we will not apply that same logic of bonding and anti-bonding to these 2 molecular orbitals. So this should be in your mind. You should not confuse it with the general idea of keeping the anti-bonding molecular orbital higher in energy. Now, if we are good to go with that thing, so let us feel the electron. So first, we will feel the sigma 1s. Okay, pair it up. Sigma star 1s, pair it up. We got 4 electrons filled in the lower molecular orbital diagram. Now, what you see here, that 1s is not the valence shell, but although it is not a valence shell, we are using it to draw the molecular orbital diagram. That means in the molecular orbital theory, we not only consider the valence electrons for bonding, but do also consider the inner core electrons. And this is the striking difference between the molecular orbital theory and any other theory that you have dealt till now. Now, let us write the electronic configuration of lithium-2. So how do we write it? It will be sigma 1s2, sigma star 1s2, and sigma 2s2. And I guess it is very clear from the MOT. So sigma 1s has 2 electrons, sigma star 1s has 2 electrons, whereas sigma 2s has 2 electrons. So therefore, we got the electronic configuration of lithium-2 molecule. Now, we will try to obtain the useful information out of this given configuration and molecular orbital diagram. So first, what we will calculate? We will calculate the bond order first of all. So to calculate the bond order, we will count the number of bonding molecular orbital electron and anti-bonding molecular orbital electron. So it will be 4 and 2 respectively. Further, the bond order will be 4 minus 2 divided by 2, which will give you 1 as the bond order. Now, the bond order is 1. Therefore, a single bond will be present between these 2 lithium atoms, and that bond will be sigma bond. Again, I am repeating this point. It's important here. You know this thing already, but when we will move on to carbon, you will see an anomaly, and that would be very surprising for you. So keep in mind that which type of bond is being formed here. So in this case, of course, your normal sigma bond is formed. So since we are getting a bond order as positive, so it will be a stable molecule with a single covalent bond between two lithium atoms. What about the magnetic nature? Again, no unpaired electrons are present here. Sigma 1s is having two paired up electron, sigma star 1s also, and sigma 2s also. So lithium 2 will be dimagnetic in nature. Okay. Now there is a small factual thing about this lithium 2. It will exist in the vapor phase. Coming on to the next molecule, which is C2. Now C2 configuration is quite complex as compared to the previous one, because now we are seeing the 2p inclusion. And what is the order here? First, sigma 1s, sigma star 1s, simple. Sigma 2s, sigma star 2s. Now we have pi 2px and pi 2py. And finally, we have sigma 2pz, pi star 2px, pi star 2py, and sigma star 2pz. Now this order is very important to remember. If we know this thing, so let us try to fill this electron. We know that each of your carbon atom contains 6 electrons. Therefore, the electronic configuration for your carbon atom will be 1s2, 2s2, and 2p2. What about the number of total electrons? It will be 12. 6 plus 6 will be 12. So we will write the electronic configuration for the C2 molecule. 1s, sigma 1s is having 2 electrons. Sigma star 1s is again having 2 electrons. Sigma 2s is having 2 electrons. Sigma star 2s is having 2 electrons. Lastly, your pi 2px and pi 2py is also having 2 electrons, right? Now we got the MOT. Let us move on to the bond order and discover that what is the surprise element in the bond order. If you calculate the bond order here, then the number of bonding molecular orbital electron are 8, and the electrons of the anti-bonding will be 4. So bond order will come out to be 2. Okay. So your 2 carbon are attached by 2 bonds. Now the question is that, are those bonds present between 2 carbon atom forming pi bond or sigma bond? So the normal case would say that there are 2 bonds. So first should be sigma and second should be pi. This is the normal perspective that we have. But if you just see the C2 molecule, first of all, it will exist in extreme condition. It has no existence in our normal conditions, right? And second important thing is they have no sigma bond between them. Both of the bonds, so bond order is 2, so double bond is there. Both of the bonds are pi bond. Now, why are we saying it? If you look at the valence orbitals, which is pi 2px and pi 2py, so the 4 of these electrons are going into the pi molecular orbital. Okay. So the sigma 2s bonding is cancelled by the sigma star 2s. Sigma 1s bonding electrons are cancelled by the sigma star 1s. But the pi 2px and pi 2py are not cancelled out. And 4 of these electrons are lying in your pi molecular orbital. So these 2 bonds will be pi bonds. Okay, it's very, very important that your carbon molecule will have no sigma bond. It will exist in extreme condition because of its absence of sigma bond. And second thing, both of the bonds will be pi bonding. But according to the normal double bond, it should have a sigma bond and a pi bond, which is not seen. Now coming on to the dimagnetic nature, because it has no unpaired electron, so it will be dimagnetic in nature. Okay. Let us move on to the next thing. So our next discussion is about oxygen. Now what do we see in case of oxygen? Instead of pi 2px and pi 2py coming here, we are first seeing the sigma 2pz. And remember student, this is the normal case. And this should be the case for the lithium, lithium, not the lithium. This should be the case for your carbon, your nitrogen. But due to the sp mixing, remember this term, due to the sp mixing, your pi 2px and pi 2py is in a lower energy as compared to the sigma 2pz. Okay? Is this clear? From oxygen onwards, we are getting the normal trend. So remember this thing. Okay. Here, each of your oxygen atom are having 8 electrons. You can count it. It is given there here. 1s2, 2s2 and 2p6. Okay, 2p4, not 6, 2p4. So this will be the electronic configuration. There will be total of 16 electrons for 2 oxygen atoms. So upon filling up the electrons in the given orbital, so first we will fill the sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then sigma 2pz, pi 2px, pi 2py, and pi star 2px and pi star 2py. Now the new thing that you are seeing is 2 unpaired electrons present in the pi star 2px and pi star 2py. So there is a change here. Till now we have not seen a molecule that is having a unpaired electron. So how do we calculate the bond order? Very simple. The total number of electrons in the bonding molecular orbital is 10 and in the anti-bonding is 6. So the bond order will be 2 here. 10 minus 6 by 2, which is 2. And both of this bond are covalent bond, and it will follow the normal procedure of having one sigma bond and one pi bond. Then what about the magnetic nature? Because of the 2 unpaired electron in the anti-bonding, which is in pi star 2px and pi star 2py, O2 will be paramagnetic in nature. So this is the first molecule that we are encountering which is paramagnetic in nature. Now let us look at the nitrogen molecule. So why I have put the oxygen before nitrogen? So as to compare both of this. If you look at the nitrogen here, you would notice now again your sigma star 2pz is at a higher energy as compared to the pi 2px and pi 2py. So here it will be sigma 2pz, not sigma star 2pz. Sigma 2pz will be in a higher energy, whereas your pi 2px and pi 2py will be in a lower energy. So this order is, again I am repeating it, it will be reversed from oxygen and it will be continued for the upcoming atoms. Okay. Now coming on to the filling of this molecular orbital diagram, we know that nitrogen has 7 electrons, where the electronic configuration will be 1s2, 2s2 and 2p3. So total number of electrons will be 14 in our nitrogen molecule, 7 coming from each nitrogen. Now what about the electronic configuration? We can write it very easily. 1s2, or I would say specifically sigma 1s2, sigma star 1s2, then sigma 2s2, sigma star 2s2, then we have pi 2px2 and pi 2py2, and lastly we have sigma 2pz2. So this will be sigma 2pz2. What about the bond order calculation? Total number of electrons in the bonding molecular orbital is 10 and anti-bonding is 4. So the bond order will come out to be 3 here. So this is a very stable molecule. You are seeing a maximum of 2 bond order till now. This is the first molecule which is having a bond order of 3, and due to this reason your N2 is very stable and it is inert in nature. And we use this thing for packaging in the food industry also, because oxygen is quite reactive as compared to the nitrogen, which is having a bond order of 2. What about the triple covalent bond? It is having 1 sigma bond and 2 pi bond according to the normal convention. Then coming on to the magnetic nature, we have no unpaired electron here, which is indicating your anti-molecule as dimagnetic in nature. Now let us do a question on comparing the relative stability of the following species. So the species are O2, O2 plus, O2 minus and O22 minus. So this is a practice question. I will give you the solution along with this, okay? So you don't have to worry about it. Okay? So first we will see the O2. We have already seen it in the previous slide. We know that higher is the bond order, greater is the stability. So this is the key point to this question. So calculating it for O2 first of all, this will be the electronic configuration. Okay, we have a sigma 2s2, sigma star 2s2, sigma 2pz2, sigma 2px2, sigma 2py, pi 2px2, pi 2py2. Then we have pi star 2px1 and pi star 2py1. Here, if you see, I have not represented your sigma 1s and sigma 1s2. Okay, so when you will be good at representing the MOT, you will also not do the, we will also do the same. Okay, just try to I would say try to eliminate the need of writing the lower inner core configuration. Okay, now for a board exams it's important to do so, but if you are doing it for a competitive exam, try to ignore the configuration of the inner core electrons. Okay, why is it so? Because ultimately the bond order will be cancelled out in the final stage. Now, what will be the bond order calculation? So 10 electrons are there if you count it for the bonding case. So this is 2 here, then 2 here. So 4, 4 plus 2, 6, 6 plus 2, 8, and 8 plus 2, 10 electrons. What about the anti-bonding? So 2 for the sigma star 1s, then 2 plus 2 for the sigma star 2s, which is 4, and 2 from the pi star 2px and pi star 2py. So 6 electrons are total in the anti-bonding case. Therefore, the bond order will be 2. What about the magnetic nature? We have seen it. If it is having unpaired electron, it will be paramagnetic in nature. Now, let us try to calculate it for the O2 plus. If I do it for the O2 plus, there is a small change for the O2 plus. What is that change? So the total number of electrons for the O2 will be 16, isn't it? So if I calculate it for the normal O2, it will be 16. 8 plus 8, 16. But here we have a plus sign upon this molecule. This indicates that one electron will be less. Okay. If there is one less electron, then total electron will be 15. Of course, it will be 15. And that electron will be removed from pi star 2py. So we are not seeing an electron in the case of O2 plus here. See, it is vacant. This position is vacant because it is containing a positive sign. Now, coming on to the next bond order calculation. Since we have removed electron from the anti-bonding, therefore the total number of anti-bonding now will be 5. What about the bond order? 10 minus 5 will be 2.5. Then about the magnetic nature. There are total of 1 unpaired electron which is present in pi star 2px. So it will be paramagnetic in nature. Now to calculate a bond order, there is a very simple trick. I will tell you this thing in the next class. But for now, I would encourage you to draw the MOTs. So this is the reason I have not given that shortcut. Because it will be difficult for you to obtain marks in the competitive exam if you are not able to draw this, if you aren't able to draw this MOT. So this drawing is very important. Okay. Now we have calculated the bond order for O2 plus, which is 2.5. Coming on to the next molecule, which is O2 minus. What will happen in case of O2 minus? There will be an extra electron. Okay. So the O2 was having pi star 2px and pi star 2py as 1 electron. Because of this extra electron, now the pi star 2px is having 2 electrons in total. You can see it very clearly. So your new configuration will be as it is up till this point, which was the case for O2. But after this, we have pi star 2px2 and pi star 2py1. Therefore, the bond order calculation can be written as 10 is the number of bonding electrons and anti-bonding electron is 7, which gives you the bond order as 1.5. See student, if we are removing an electron from the anti-bonding, we are getting a bond order of 2.5. If we are increasing an electron in the anti-bonding, we are getting a bond order of 1.5. So increasing the electron in the anti-bonding is decreasing your stability. So we are seeing a decrease in the bond order. Okay. And for the normal O2, which is having an intermediate number of anti-bonding electron is having a bond order in the mediate one. So it is 2. What about the magnetic nature? Here also we have one unpaired electron in the pi star 2py. Therefore, O2 minus will be paramagnetic in nature. So we have seen O2, we have seen O2 plus, we have seen O2 minus. Now let us move on to the O2 minus. Your task would be to remember this name. It's very important. O2 minus is called as superoxide. O2 minus is called as peroxide. Then moving on to the O2 minus. So for O2 minus, there will be addition of 2 electrons in the normal O2 molecule. So pi star 2px will also have 2 electrons and pi star 2py will also have 2 electrons. Therefore, we got our configuration, a change in the pi star molecular orbital. Now what we can write? We can calculate the bond order. So total number of bonding electrons 10, anti-bonding electrons is increased by 2. 6 was in the case of O2, 5 was in the case of O2 plus, and 7 was in the case of O2 minus. But in the case of O2 minus, it is 8. Therefore, you will get your bond order as 1. So this is the lowest bond order that you have seen till now. What about the magnetic nature? There are no unpaired electrons. You can see it very clearly. All the electrons are paired up here. Therefore, O2 minus will be dimagnetic in nature. Then if we write about the bond order, since your O2 plus is having the highest bond order, which is 2.5, it will be the most stable one. Then your bond order of 2 is for O2. Then 1.5 was for the O2 minus. And for the O2 minus, it is 1. Now let us move on to our next topic, which is hydrogen bonding. So what is hydrogen bonding? It is basically an interaction. It is not a bond, first of all. It is an interaction between the hydrogen atom of one molecule with an electronegative element. Now there are conditions to it. Every hydrogen is not capable of doing the hydrogen bonding. So what are those criteria? We will see it. Let us try to understand this definition with the help of HF molecule. If you look at the HF molecule, then it is having a covalent bond. Okay? And due to the extra electronegativity or high electronegativity of fluorine, it is bearing a delta negative charge, whereas your hydrogen will bear a delta positive charge. Then if you consider 2 molecules individually, they will attract each other because your fluorine is having a delta negative charge and the other molecule which is having a hydrogen, it is bearing a delta positive charge, and therefore they will interact with each other due to electrostatic interaction. And this interaction will make them to come closer to each other and set up a force which is called as hydrogen bonding. This hydrogen bonding is represented by this dashed line, and for the hydrogen fluoride, it can be represented as this figure. Okay, so we have one hydrogen fluoride which is bonded covalently. Then we have this another molecule of HF. These both molecules are being attached to each other by the dotted lines. Okay, so fluorine is having delta minus and the other molecules, hydrogen is having delta positive. Therefore, we are seeing a Coulombic interaction between all of these molecules. And this is creating a linear chain. Okay, not a linear one, I would say. Appropriately, I would say a zigzag type of structure is being obtained on interaction. But remember this, student, it is very important. Your hydrogen bonding will be weaker than your van der Waals force. Sorry, covalent force. Okay, but it will be stronger than the van der Waals force. So this is very important line. Your hydrogen bonding is weaker than the covalent bond, but stronger than the van der Waals force. Now, I said you there are some criteria for the hydrogen to do a hydrogen bonding. What is that criteria? So the hydrogen which is capable of hydrogen bonding must be connected covalently to a electronegative element, and specifically 3 electronegative elements. Those are fluorine, oxygen and nitrogen. If your hydrogen is attached directly to these any of these three elements, then and then only it will be capable of doing a hydrogen bonding. Okay. Yes, you can say that if this is a dipole-dipole type of interaction, but in the case of this hydrogen one, there is a specific increase in the interaction. And due to this high degree of attraction, we are keeping it in a different league, which is hydrogen bonding. So the size of electronegative atom should be small. So this is the basic criteria: fluorine, oxygen, and nitrogen. Now there are two types of hydrogen bonding, which is intramolecular and intermolecular. Intermolecule is between two different molecules, okay? And the atoms that are forming, again, they should be attached to either fluorine or oxygen or nitrogen. So we can take the example of HF, H2O, and NH3. Here we have already seen the intermolecular hydrogen bonding case, where one of the molecule is doing a hydrogen bond with the other molecule. No, chlorine will not be able to do so. Okay, so if your hydrogen is attached to a chlorine, it will not do the hydrogen bonding. Never do it. It's not possible. Similarly, if you take the case of water, then the oxygen of one molecule of water is interacting with the hydrogen of other molecule of water. Now let us look on to the next type of hydrogen bonding, which is commonly seen in the organic molecules, which is called as intramolecular hydrogen bonding. So in this type of hydrogen bonding, your interaction is set up between the atoms of the same molecule. Examples are orthonitrophenol and salicylaldehyde. So we have a diagram here to represent the same. Now I am leaving the task of seeing the intermolecular attraction for the salicylaldehyde by yourself. So for the nitrophenol, orthonitrophenol, you can see that your oxygen is doing a hydrogen bonding with the hydrogen which is attached to oxygen, right? So there is a hydrogen bonding. Okay. So this is a case of intramolecular hydrogen bonding. So this was all for today's class. Thank you for attending the session. I hope you enjoyed it. Now, before moving on to the next class, I am giving you a small briefing about yesterday's class. Okay. So that is basically about your, say, the molecular orbital theory basis. So there was a mistake in previous class. I would say that was not a mistake. There was a misunderstanding. So I will try to explain it to you in a proper manner so you won't confuse it. So just wait for a while. I will switch on to the board to explain the same.